So hello everyone, and welcome to Applying the Law of Universal Gravitation. Yesterday we discussed how Sir Isaac Newton, in what is perhaps an apocryphal story, supposedly was sitting under an apple tree in his orchard outside of Cambridge, and he saw an apple fall from the tree. And seeing that apple fall from the tree, he knew that the force which caused the apple to fall was gravity. And he said, perhaps that force of gravity is the same force that keeps the moon in its orbit around the Earth. So he extended the idea of gravity out to the heavens. And from that, he then developed an idea which we now call the law of universal gravitation. The law of universal gravitation, with a little help from Lord Henry Cavendish, is now written as the force of gravity is equal to the gravitational constant times the product of the masses divided by the separation between the objects squared. So again, in this equation, r is the distance from center to center. It came about because of the radius of the orbit of the moon around the Earth, but it's really distance from center to center. And g, again, discovered by Lord Henry Cavendish, the gravitational constant, or 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And again, this is a universal law. So Newton extended this even beyond the Earth and the moon. He said perhaps any two masses in the universe would attract one another with a force given by this equation. And that means any two masses, perhaps even you and the person sitting next to you, actually are attracted to one another with a force of gravity as given by this equation. Now, you might say to yourself, well, wait a minute. If I'm attracted to every other thing, why are we not all just coalescing? Why are we all not just coming together? Let's do a little problem here. Let's say you have a 50-kilogram student. By the way, that's about 110 pounds. Is a meter away from a 75-kilogram person. That's like 170 pounds. Okay, so we got a 110-pounder and a 170-pounder roughly, about a meter away. According to this equation, what's the force of gravitational attraction between them? Well, here's the equation. Let's plug in the numbers. The gravitational field strength, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. The product of the masses, 50 kilograms, 75 kilograms. The separation in between, 1.0 meters squared. Notice that the meters squared cancel out with the meters squared. The kilograms squared cancel out with the kilograms squared. We get a number of newtons. 2.5 times 10 to the negative 7th Newton. Now remember, a newton is a little less than a quarter of a pound. So we're talking 10 to the negative 7th here. This is an extremely small force. So the force of just the air resistance, the friction between you and your chair, is so much larger that you don't really feel this force. In order for this force of gravity to really be big enough for us to notice, we need some pretty big masses here. Need some pretty big masses to overcome this 10 to the negative 11th in this very small gravitational constant. Which, by the way, is why it took 100 years for Cavendish to figure out how to do the lab, because this is a really fine lab, right, in order to be able to come up with this really small constant. So there are forces of gravity between you and everything else in the room. It's just that they're so small that you don't really notice them. Second thing. Let's look at this apple. Consider this apple at a distance, the radius of the Earth, from the center of the Earth. If we drop this apple at the surface, right, of course it will fall because of the force of gravity. And we've done this analysis before. We can look at the acceleration with which it falls by using Newton's second law. Net vertical force is mass times acceleration. The only vertical force is the force of gravity. If we're neglecting air resistance, it's down, which makes it negative. The acceleration is also down, which makes it negative. This is the mass of the apple. And of course, we know, and Galileo knew before Newton, that the acceleration of free fall is little g. Technically 9.8 meters per second squared. However, now we also know that there's another way of writing the force of gravity acting between the Earth and the apple. And that is the gravitational constant times the product of the mass of the Earth and the mass of the apple separated by their separation squared. And if this apple is essentially at the surface, the separation from the center of the Earth to the center of the apple is essentially the radius of the Earth. Now notice here, the negatives cancel. The mass of the apple cancels. And we can then solve this equation for the mass of the Earth. Multiply by the radius of the Earth squared, divide by the gravitational constant. Plug those numbers in. G, as known by Galileo, 9.8 meters per second squared. The radius of the Earth, actually known since the ancient Greeks, or a decent approximation, 6.38 times 10 to the 6th meters, which is squared. You'll notice that with these forces of gravity things, these big universal things, you need to get used to using scientific notation. Don't lose the squared, by the way. And the gravitational constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And therefore, the mass of the Earth, just 3 sig figs, is about 5.98 times 10 to the 24th kilograms. This was something that Henry Cavendish published, and so he's credited with being the first man to quote-unquote weigh the Earth. Actually, he massed the Earth, right, as opposed to weighing it, but he was the first one to be able to figure out the mass of the Earth. And notice he did it without actually putting the Earth on a scale or a balance or something like that. He did it by applying this law of universal gravitation to something at the surface of the Earth. Now, what if the apple isn't at the surface of the Earth? Up till now, we've confined ourselves to being near the surface of the Earth, where the acceleration is negative 9.8 meters per second every second. What if we're a significant distance away from the surface of the Earth, so that now we have a separation we can call r? Well, there still would be only one force acting on the apple. That would be the force of gravity. So the net force is equal to mass times acceleration. That's negative f of g equals negative mass of the apple times the acceleration due to gravity. And notice I'm not going to use a little g here, because that's only at the surface. This is the acceleration due to gravity. Well, negatives cancel. Force of gravity we can write as gravitational constant, mass of the apple, mass of the Earth, which I'm going to call capital M, it's kind of traditional, divided by r squared, where r is the separation from the center to center. Notice that the mass of the apple cancels out. The reason it does, more mass, bigger force of gravity, more mass, more inertia, more resistance to the force of gravity, more resistance to changes in its motion. And those two things, as they often do, cancel out. So, here is an equation we can use to find the acceleration due to gravity at a distance r from the center of any planet, so long as we realize that this capital M is the mass of the planet. And that's important to realize. This is not the mass of the thing that's in free fall. This is the mass of the planet, right, that's causing the gravity. Notice that the gravitational acceleration, or the gravitational field strength, would be the same equation, is proportional to the mass of the planet and inversely proportional to the square of the distance between. This sounds like something that would work with a good MOP. Oh, it will. Now, special case, what if we're at the surface of the Earth? Well, then the mass is the mass of the Earth, and the distance is the radius of the Earth. Plug those numbers in, and of course, what do you get? You get 9.8 meters per second squared. Now, if you're saying to yourself, Mr. K, that sounds kind of circular. We used 9.8 to find the 5.98 times 10 to the 24th kilograms, and now we're using the 5.98 times 10 to the 24th kilograms to figure out 9.8. Heck yeah, it's circular. But of course, physics has got to be consistent with itself. So there is a little discussion and a few consequences of the law of universal gravitation.